Welcome back to lecture on drone systems and control. This particular lecture is on a very interesting topic which is being used in safe path planning and navigation of autonomous systems for last decade. It is known as control barrier function. So in this particular lecture we will go through the idea and concepts behind control barrier function. We will try to see that how it is mathematically conceptualized. Then we will go through its operation, some mathematical results which are involved in the development of control barrier function. Then finally we will see what are the advantages and limitations of control barrier function, and we will provide some reading materials so that you can go through the seminal concepts involved in control barrier function. Okay, so with this I'll start. First I will highlight the motivation behind control barrier function in this lecture. I'll define safe and unsafe set, which is very important, and from the perspective of a drone or any autonomous systems, what can be a safe system and what is an unsafe system, that we'll understand. We'll talk about affine control systems. We will define safe and unsafe sets with the help of control barrier function. We'll talk about some mathematical concepts like forward invariance, class K functions. We'll talk about safety guarantees. Interestingly, we'll see that control barrier function can mathematically guarantee safety of a vehicle, or can guarantee that the particular vehicle will never collide with obstacles mathematically. Okay, we'll talk about quadratic programming problems with CBF constraints, and then we'll talk about the advantages and limitations. Okay, fine. So you see that the limitations of a traditional control methods are that they focus more on stability and other performance metrics. Like in the last module on drone control, we have seen that there are certain performance metrics like rise time, then settling time, maximum overshoot and all. The point here is that those which are very classical controller methods, they can take care of different performance metrics and focus on the stability of the system, but they do not explicitly enforce safety constraints. Okay, let me tell one thing, that when we talk about safety in this particular lecture, we mean collision avoidance. Okay, if a vehicle, specifically a drone, goes and collide with one say obstacle, then it is not safe, right? It is not safe for the system. There can be some accident due to that. The drone will also get damaged, so there is a risk of property damage as well as the vehicle damage. So safety is very important, and when we talk about control barrier function in this particular lecture, we will talk safety in terms of obstacle avoidance. Okay, now control barrier function can provide a formal mathematical framework to enforce safety. Okay, it is applicable in nonlinear systems which has certain constraints, system constraints like input constraints, state constraints, something like these. Then it can be integrated with optimization based controllers. So control barrier function can be used or incorporated in real time quadratic programs, which is a optimization problem, and then we can get the safety critical control by solving the optimization problem. Okay, finally, which is very interesting but will not be covered in this particular lecture, is that control barrier function can be extended to higher order or higher relative degree safety constraints, and in that way it provides a flexibility that it can handle higher relative degree systems as well and impose safety. Okay, so what is control barrier function? It is a mathematical tool, fine. It is used in control theory to guarantee safety mathematically, fine. Ensure that certain state constraints are always satisfied over time. What are the states? We will see. It acts as a barrier that prevents the system from entering unsafe regions of the state space. Okay, so if we want to summarize, we will say that it is a function that creates a barrier between safe and unsafe set or region, and then helps to generate control input to avoid the unsafe set. That means it will help the vehicle or it will algorithmically or mathematically develop the control inputs for which the vehicle or drone will never enter the unsafe set. Okay. Okay. Let us define safe and unsafe set now. For a drone, what is unsafe set? It is a set that constitutes of obstacles, walls, say electric poles, buildings, etc. Right? It can be electric wires as well, because that also can create problem in a safe path planning, right? Then what is safe set? Safe set is the entire area or arena or entire space excluding the unsafe set, right? So safe and unsafe set are very important concept in control barrier function, and when we talk about the barrier, that barrier actually like forms the boundary between the unsafe and safe set. Okay. So when we talk about control barrier function, it can be distance between drone and the obstacle, or it can be the angle between the obstacle position and the vehicle heading. Okay. So when the distance, if you see the right hand image, see the drone with its sensor finds one obstacle, okay, which is say orange in color. Okay. Around that we have a boundary. It is called safety tolerance. What does it mean? It means that if the drone somehow crosses this boundary, then it will be very difficult for it to turn properly for its turning constraints, and eventually it will anyway hit the obstacle. So the drone cannot just go till the obstacle. Before a certain distance it should stop. So this is some indicative distance and not measured with the turning radius constraints and all. Whatever I see here is just to indicate the idea. Okay. So when this is say safety threshold or tolerance, so when the distance is greater than distance of the drone from the obstacle is greater than this particular threshold, that means outside this boundary, then we say that it is a safe set, the drone is inside a safe set. But if it is less than threshold, that means the drone somewhere comes at this point which is inside the safety tolerance or safety boundary, then we say that it is in unsafe set. Okay. Similar situation can be seen for two drones if they are crossing their path, then also at some point of time they will be encountering some unsafe set, so that they should avoid by keeping themselves inside the safe set. Okay. So I would give one example of control barrier function in drone systems. As I have already told that the distance, that means say just assume that in a network this is the ith drone. Okay. So its position is this and the obstacle has a position this. Okay. Now if we calculate the distance between the drone and the obstacle and then subtract the tolerance region, that means it is some distance like this, then this can form a control barrier function, right? So what will be the objective then? Then the objective will be to keep h1p greater than 0. Okay. When h1p is greater than 0, then we will say that it is in safe set with the control barrier function h1p. If it is equal to 0, then we will say that the drone has come on the boundary, and somehow if the drone crosses this boundary or safety tolerance or threshold and goes inside, then it becomes less than 0. Okay. Similarly, when it is a drone pair, just assume that this is the ith drone and this is the jth drone, then they have the distance among them like this, and we have a safety tolerance region which might be different for from a drone obstacle pair. Accordingly, we can form the drone pair control barrier function, which is h2p, and accordingly the idea will be to keep it greater than 0. If it is less than 0, then we can conclude that the drone has entered the unsafe region. Equal to 0 is also challenging because then we have to see that whether the avoidance algorithm, sense and avoidance algorithm is working properly or not. Otherwise, equal to 0 is on the verge of being into the unsafe set. right? Okay. Okay, I'll show by one animation that how the control barrier function comes into picture in a drone navigation. Just assume that the drone comes into this particular area, and with its sensor it detects a no fly zone which is unsafe set. It can be some building, it can be some restricted area, can be a monument or an electric pole, anything it may be. Okay, so what it will do with its sensor, it will try to find the points on the no fly zone. Okay, like leader rays, you have gone through leader in the sensor lecture, so you know that the leader has the point clouds in its detection. So these are kind of the point clouds which are on the obstacle, right? So these points on the obstacle are, say, gives the boundary on the obstacle, and the drone should not come till this point. But at the same time we have to consider another fact, that is the turning radius of the drone sufficient enough so that it can come very close to these red points and then turn safely? It may not be possible, right? So the drone, according to its turning radius, the safety tolerance set or safety tolerance boundary can be formed. Okay, so the red points are called unsafe sample points, or if you come till this point then it will be collision. But if you come till blue point, you are safe, because the turning radius is sufficient for the drone so that it can turn and then cross the obstacle by moving on the tolerance boundary. Okay, so these blue points are safe sample points, where it is safe to maneuver without collision. Maneuver means what? It should turn, it should change its motion, direction of motion, and beyond this point the drone becomes unsafe because it enters the unsafe region, right? Okay, so what is unsafe set? For unsafe set, the control barrier function will be less than equal to 0. It is we say it is strictly unsafe when it is less than 0, right? So what we can conclude is that the drone can come till this point and then it should maneuver, right? Okay, now we'll define the control barrier function mathematically, and there is a process. We have to know certain basic things mathematically, then the theory on control barrier function will be developed. Okay, so here we define a control before defining a control barrier function, we define one affine control system. Okay, what is affine control system? It is of this form. So it is a non-linear system, or it can be a non-linear system, but affine in the control input. Okay, this means it is affine in control, that means linear in control input u, though f and g can be non-linear in x. Okay, if we go back to the study on state space analysis, we have seen that when it's a linear system, then it can be represented as ax plus bu, right? When it comes to a non-linear system, we can write the system as x dot equal to fx, or it can be a function of control input as well. But when it is a affine control system, then it should be written as this form. That means the system, we should be able to represent the system equation in this particular form, otherwise it is not a control affine form. You can verify that x dot equal to ax plus bu is also in a way a control affine form. Okay, fine, but this is a linear equation, so we don't specifically talk about control affine system when we talk about linear equations and linear time invariant systems and their state space representations. So when we talk about nonlinear systems, then affine control systems play a very major role in lots of systems and its analysis. We have to be careful whether we are defining the system like this. Okay, I would suggest the reader or students of this course to check that the drone equations can also be represented as affine control system. Okay. Now x is a system state, u is the control input for the system, or we should say that x is a system state vector. This is control input vector. Fx is uncontrolled dynamics. Why we say that? Because if the system is just x equal to fx, you see that there is no control input. So if the system is it is an autonomous system without a control input. So if somehow the system is not stable, not safe, by changing or varying the control input adequately, the system cannot be controlled. That's why we say that it is uncontrolled dynamics. And what is Gx? Gx is the control effectiveness matrix or vector, whatever. How the control affects the system is represented by Gx. Okay, that's why the term when it comes Gx into u, this Gx actually incorporates or somehow introduces the control input into the system. Okay, so I think this part is clear, and you by this time you know what is a control affine system. Okay, fine. Now we will define sets with control barrier function. So in the previous slides we have seen that we can define a control barrier function like this. Say this is a distance function, right? What it is? It is the distance between the drone and obstacle minus some safety tolerance, right? And we have also seen that when hx is greater than equal to 0, we say that it is safe. Equal to is the boundary of the unsafe and safe region, and what is the interior of the set? The set interior is when hx is greater than 0. So if we want to tell it pictorially for a problem where say we want to define a control barrier function which is a distance function for a drone, then how it will look like? Just assume that this is the obstacle, right? Now if this is the obstacle and say this is the safety tolerance radius, say this is r, right? Then if the drone is here, this is the total distance between the drone and the obstacle, and that is represented by this term minus this r. That means it becomes effectively this much of distance, right? So we see that when the drone is outside the tolerance area, then this particular distance is of course greater than 0. That means hx is greater than 0. When it comes on the boundary, then hx becomes 0, because that time distance of the drone and obstacle is equal to r. So at that point of time hx becomes 0. Then it is clear that if we define a set like this with a control barrier function, then hx greater than equal to 0 actually defines the set which is the entire set out of the obstacle and the tolerance region, right? Then what is the boundary of the set? It is on the boundary of the tolerance region. And what is the interior of the set? When the drone is away from the boundary as well, right? Okay. So if you have difficulty in understanding what is the interior of a set and what is the boundary of the set, then you just go through some very basic textbooks on real analysis. You will have a very fair idea. Okay. For just to keep the content concise, we are not going through the set theoretic concepts and all in this particular course, but I encourage you to see this in a great details. Okay. Now we say that h we are talking about is a continuously differentiable function. Okay. Now given a closed set C that belongs to say a subspace Rn, n dimensional subspace, we determine conditions on a function, say this should be h, okay, which is inside the interior of C to mapping into R. such that the interior of C is forward invariant. Now this becomes another important concept, that what is forward invariance. Okay. In the next slide we will see what is forward invariance, which is very important and significant topic to understand control variable function. Okay. What is that? You see, a forward invariance refers to a property of a set. Okay. So we will say that a set is forward invariant when, if the system starts in that set, it stays in it for all future time under given dynamics of the system and the control input u, right. Okay. So this is the set C. It is a safe set. We know that if we define it like this, Hx is greater than equal to 0, and if okay, I am taking it in the point of distance based control variable function, and we are defining it like this. If we get into other forms of control variable function, then also we have to ensure that this property holds. Okay. Now what is forward invariant? A set C is forward invariant under a control law U if x 0, that means the initial state of the system inside the set also implies that at any time in future the trajectory of the particular system will be inside C. That is, the trajectory never leaves the safe set once it starts inside it. Okay. So if I see it from a drone perspective, we will see how it works. Just assume that this is the obstacle. So this is the safety tolerance. Okay. Now our objective is to keep the drone in a safe set, right. What is the safe set? It is the entire set, say A, excluding this particular set, right. Say this is some set S. Okay. So what C we are talking about with this is the set inside, right, which excludes this set S, that means the tolerance region and the obstacle itself, from the main set A, right. Now if the drone is here, say here, say this is the drone, the idea is that if the drone starts in this set, okay, that means the set C, then the forward invariance should be ensured in the terms that it never leaves its set C. What does that mean? Just assume that this is the boundary where the drone is expected to be, so it should not leave that set, and also it should not enter into the set S, that is also not granted. So if the drone initially is at X at the set C, where C is the set A minus the set AS, then it should be inside the set C for all the time when it is functioning. Okay. So the initial state inside a safe set will also take care that the future states are also in safe set C if the set is forward invariant, right. So forward invariance of a set C is a very important property. If we can say that a set C is safe and it is forward invariant, then we can without confusion tell that if the drone is inside set C, it is initially safe and later also it should not leave the set, so it remains safe. Okay. Okay. So what is the importance of forward invariance? It is explicitly designed to enforce safety constraints over time. Okay. What is the time? You have gone through the idea that at t equal to 0, if the set is the trajectory of the state or the state of the system is inside the set, then for t equal to greater than t greater than equal to 0, that means any time in future when the drone is functioning, it should be inside the same set, right. So the system must never violate the constraints such as staying inside or within the physical limits. That means it should be inside the area and should not leave it. Okay. It might have some physical limits like turning radius, speed and all. Okay. So those things also should be satisfied. Fine. Second thing is that it should avoid collisions. If there is a obstacle inside with a tolerance region, then keeping in mind about the turning radius or turning capability, the drone should be able to avoid the collisions, and it should respect the workspace boundaries. That means this one, it should not go out, because the drones are not supposed to be anywhere. It has certain restriction that where we can fly a drone and all, so we have to obey the workspace boundaries as well. Okay, so forward invariance, if we can ensure, it can take care of all this, it should take care. Okay, so to achieve this, the control barrier function has to enforce forward invariance of the set. Okay, what is the geometric intuition? If you imagine the safe set C, safe we are telling, safe set C is in a fenced area, okay. Forward invariance ensures the system, like a robot or drone, never breaks through the fence, so it should not go out. Even if it's at the edge, the system is steered back inward or kept on the boundary, and that is true for the obstacle as well. If it is on the safety tolerance boundary, there should be a control input that will steer the system back inward again inside the safe set, or it can be on the boundary, but depending on the functionality or operation of drone, it might not be always visible. So it should move away from the unsafe set. Okay, fine. Now there are two important concepts of class K and class K infinity functions. I would just define it, and I encourage the students to go through the material to have deeper understanding. So a continuous function alpha defined like this, with this value a greater than 0, is a class K function if alpha 0 is equal to 0. That means the initial value of the function is 0 and alpha s is strictly increasing. Okay, fine. Some variable s, alpha s should be strictly increasing. Okay, it does not have any direct correlation with the Laplace variable s, just take it as a independent variable. Okay, the properties alpha s greater than 0 for all s greater than 0, which shows that it should be strictly increasing, and this is the property for it, and it measures how the state variables affect the stability or safety. Okay, there are certain examples you can carry out and check whether these are the examples of class K functions or not. Okay, now when we talk about class K infinity functions, then the value of a becomes infinity, and then we call it as class K function where alpha belongs to k. That means an alpha, if it is a class K function, if it is a class K infinity function, then primarily it should be a class K as well, and alpha s tends to infinity as s tends to infinity. So it's a class K function that grows unbounded. Okay, the properties are that it describes the function that grows strictly and without bound, imported in global stability proofs. Okay, these are some examples. You can check first that these are class K functions, because a class K infinity function is also a class K function, and then check the rest of the things, that whether it grows unbounded or not. Okay, fine. So class K and K infinity functions in control barrier function acts like a barrier strength. It ensures the correct behavior near the boundary. Hx equal to 0 corresponds to the boundary that we know, boundary of the safe set. So the function alpha hx ensures that if the system reaches the boundary, dynamics are directed inward, keeping the system from leaving the set. That means it also imposes on the forward invariance. Okay, the choice of alpha affects how quickly the system reacts to approach toward the unsafe region. So if it is steeper alpha or steeper K infinity function, then there will be a more aggressive pushback, and if it is a gentle alpha, then there will be a smoother control near the boundary and it will be pushed accordingly away from the unsafe region, right? Okay, now we define control barrier function. Given a set C which belongs to one n-dimensional subspace R, C is a subset of Rn defined by a continuously differential function h for the system x dot equal to fx plus gxu, that we assume first. Okay. Now we say that the function h is called a control barrier function defined for the system, this system, if there exists a extended class k function alpha, that means k infinity, such that for all x in this particular subspace the following inequality holds, that is LFHX plus LGHXU plus alpha hx is greater than equal to 0. So, this actually specifies the rate of change of the system. How? When we talk about LFHX, it is actually del h del x into fx. When we talk about LGHX, it is del g del x, sorry, it is del h del x into gx. Okay, that is these two terms actually show the rate of change of h or control barrier function in the direction fx and gx, and that is the advantage of control affine system, that in this particular thing also when we take the rate of change of h in the direction of fx and gx, it still remains control affine, right. So, that is an advantage of taking control affine system. Okay. And this is the extended class k function which has the say argument of hx. Okay. This condition implies there exists a control input. So, okay. So, if the following inequality holds for the function h with all these extended class k function alpha and all, then there exists a control input u that keeps the system within a safe set. Okay. So, if the system is within the safe set forever, then in a way it ensures forward invariance as well. Okay. Fine. So, what is a control barrier function theorem? It tells that a control barrier function theorem provides sufficient conditions under which a control input exists to render a set forward invariant, thereby ensuring safety for control affine nonlinear systems. Okay. So, we have control affine nonlinear systems, we can define a control barrier function like this, where this inequality holds, then we can say that a control input exists to render a set forward invariant. Okay. So, let hx be the function, continuously differentiable function, x is in belongs to this particular n dimensional subspace. If there exists an extended class k function, or sometimes extended class k function is referred as this also, then the following inequality holds. Okay. Now, if the following inequality holds, then the set C, which is defined as hx is greater than equal to 0, is a forward invariant set under any control input measurable. Okay. Then this set, this particular thing should be also be satisfied. Okay. So, what is the notion here? Let hx be a continuously differentiable function. If there exists a class k infinity function alpha such that this particular inequality holds, then set C is forward invariant under any measurable control input ux satisfying this particular inequality. Okay. So, if we can find such control input ux that satisfies this particular inequality at all points in the set C, then any trajectory starting in C will remain inside C. Okay. So, the forward invariance for a safe set also guarantees the safety for the future time. Okay. Fine. Now, so this becomes, this particular inequality becomes the CBF constraint which should be satisfied by the control input, so that it can keep the system inside the safe set forever, right. So, CBF is this particular function that generates forward invariance of the set. That set is defined by this C equal to this. Okay. CBF condition is like this, and it ensures safety by keeping the state within C over time. Okay. Fine. Now, what to do with the control barrier function? It will ensure that the system will be inside the safe set. Fine. But which control input we need so that we can, or the system can be steered inside the safe set and it never enters the unsafe set. For that, we need one optimization problem to be solved. For control barrier function, the kind of optimization problem we solve is called quadratic programming problem. The objective is quadratic here, like this. There can be some linear term as well, but the constraints will be linear. Okay, this quadratic programming problem is by nature a convex optimization problem. That means it can be solved in a polynomial time, that means in real time, which is very important for drone functionality. If the optimization takes solving the optimization takes long time, then the drone reacting quickly after seeing an obstacle or a no-fly zone will not happen. The reaction time of the drone might be very long, and by that time it can collide or the performance can degrade, right? So, we have to solve one quadratic programming problem with CBF constraint. So, in our case, the control objective function of the quadratic programming problem is something like this. U is the control input which we want, which should be in the m dimensional subspace. U nominal is a desired or nominal control output, might be for trajectory tracking or something like this. That means there is another nominal control which is there for stability of the drone or for tracking a desired trajectory for the drone. So, that U nominal will be there, but we need another control input U for safety, and this difference should be as minimum as possible. Okay. Now, nominal control input can also be coming from a concept called control Lyapunov function. This is out of the scope of this particular lecture, but in the reading material it is demonstrated very nicely, so the readers can go through. Okay. There can be some other constraints inside the quadratic programming problem. That means there can be optional input bounds. That means what? The control input U might be inside a bound, say U max and U min. What can be the control input for a drone? It can be, say, certain its angular acceleration or something like this. So, we should have a bound on this. Okay. The CBF constraint ensures forward invariance of the safe set. Okay. This one. And the quadratic programming finds the closest admissible control input U, which is closest to U nominal, so that this minimization happens and still it guarantees safety. Okay. So, U nominal is very important because it is serving another purpose, but that might not be enough for safety. So, we need another control input which is closest to U nominal. So, this minimization is required. Now, that input, what it will do? It will serve as a control input for the safety constraint. Okay. So, if we solve this particular quadratic programming problem, then we will get the output as a control input U star. Okay, U star, which is the control input to be applied on the drone when it is on the verge of going inside a unsafe set. Okay. So, for this U nominal part, we can have a different level of control. That means there can be a nominal performance controllers like PID control, like model predictive control or feedback linearization, and additional in addition to that, there will be another safety filter which is coming from the quadratic programming problem. So, when we have a nominal performance controller, we have the U nominal, which is helping the particular drone to maybe tracking a predefined or desired trajectory, and quadratic programming solving the QP will give you another U. Okay. Or U star. What is U star? It will minimize the difference between U and U nominal square, since it is a quadratic programming problem, subject to certain constraints like safety constraint, stability constraint, control input constraint, and also another constraint can be there which is not mentioned here is the system constraint. That means the system is represented as fx plus gxu. So we should have the control input u that satisfies the state equation also. Okay. Now, why affine control system is required? You have seen that when we take the rate of change of control barrier function, then also we get it in a very nice form. Okay. So, affine control structure is essential because the CBF condition becomes linear inequality in U. This allows efficient computation of U using quadratic programming problem, and this ensures a real time implementability in safety critical systems. Why? Because it is a convex optimization problem, it can be solved in real time. Okay, fine. What if the system is not affine control? It leads to nonlinear constraints in U. Then the convex optimization can get transformed into a non-convex optimization, which is computationally more expensive and cannot be solved in real time, and there is no guarantee of finding a feasible solution. So that is also important. We have to see that in a quadratic programming problem, that whether we are getting a feasible solution or not. If we don't get a feasible U star, then what to implement as a control input on the drone so that it comes out or never enters the unsafe set. Okay. How CBF ensures forward invariance? So given a control affine system x dot equal to fx plus gxu and a control barrier function hx which satisfies this particular inequality with a control input u for a class k function alpha. Okay. This condition actually ensures that hx 0 is greater than 0, then hxt is also greater than 0 for all time t greater than equal to 0. So by this and from the CBF theorem, it ensures that it will be a forward invariant system, and hx 0 equal to 0 means that the system can remain on the boundary or move inward, but never violate the safety constraint. Okay. Thus it makes the safe set C invariant under the system dynamics. Okay. CBF ensures that once the drone is outside the no fly zone, cannot enter it under the controller. So mathematically it will be guaranteed. Okay. What is safety guarantee? The safety guarantee is that when the drone is inside this particular set C and we have this as a control barrier function which has say the property that it is continuously differentiable, then there is a control input u, then there is a class k function alpha. With all these constraints, we define a safety constraint with the control barrier function hx, right? This set C represents safe set. How? Because of this part. Right. Now, if xt, that means the system trajectory or system state is inside set C, then the system never violates the safety condition. That comes from the CBF theorem, right? So this is exactly what forward invariance guarantees. So we are telling that the C is a safe set. That is how we define it. We use H as a control barrier function with this particular control input. Then forward invariance is guaranteed, and since C is a safe set, then we can say that the system will always be inside the safe set from the definition of forward invariance. Okay. So ensuring forward invariance of C means ensuring safety. C is inherently safety, that is what we are defining. We have the forward invariance due to the definition of control barrier function. So a forward invariance inside a safe set ensures safety. Okay. This is just like very basic simulation to show that how control barrier function will work. Here it comes from this is a start position S and this is a goal position G. The drone starts moving. I am showing it in 2D, that means you can consider it as a top view. Okay. Now there is certain boundary or tolerance region just around the particular obstacle. So it takes a turn like this. So at this point the U star is required. Okay. Before that it was coming under say this portion. This portion is due to the nominal control, that might be a PID or MPC, which like is expected to take the drone to the goal position like this. Okay. Under a nominal control, this trajectory, which is a predefined trajectory, that should be tracked by the drone under the nominal controller. But when it encounters the particular boundary, or when the sensor tells that now you are on the verge of being in the unsafe state, that time the quadratic programming problem will be solved, which tries to minimize the difference between u minus u nominal. Why it is required? Because we do not want the control input in such a way that it takes a very like aggressive maneuver, it goes something like this, because that will become very much energy consuming. So we should be minimizing the energy, which is this difference, and at this point of time it should get the u star out of the quadratic programming problem. With this u star, it is first doing the maneuver. Okay. So this maneuver, it comes here, it should then again come back to this particular trajectory maybe, or it should from here go like this to the goal, but it encounters another obstacle, which is the second obstacle, right? For that it goes like this, it encounters another obstacle, which is obstacle 3, so it crosses that also or avoids that also, and then finally goes straight to the controller. Okay, fine. So this is a kind of simulation based demonstration that how the control barrier function will work. Okay, we'll see the advantages of control barrier function. It gives formal safety guarantees mathematically. It can be integrated with other performance objectives which are being delivered by the nominal controller. There is a real time implementability due to the convex optimization. Quadratic programming problem is a convex optimization problem. Okay, it is robust to noise and uncertainty. The control barrier function can be designed like that. Scalability to high relative degree systems. This I encourage the students to read with more details. We have seen that the CBF theorem ensures forward invariance with a properly designed control barrier function. So forward invariance in a safe set gives us safety guarantees. Then there are linear constraints, easier to handle, tractable optimization, quadratic programming problem, and finally we can somehow integrate the safety and stability aspects. Okay. Limitations: if the optimization becomes infeasible somehow, then that's a problem, right? Then input constraint conflicts can come, that one control input should be say less than some maximum value and greater than something else. Another control input can be can have a different level of constraint, so that can have a conflict, and then the solution can become infeasible to get. Then there can be some deadlock and local minima. Please read about it. Then obstacle geometry restrictions are also there. Sometimes that can create a problem. We have to be careful. Computational complexity can go high if we are proposing a very complicated control barrier function. Then there is a model dependence. Without model, it cannot work. We need this model, right? Then there can be estimation error, and if there is some error in the sensor, then that also should be handled separately, that only control barrier function cannot guarantee. Then the problem is that if there is a non-convex obstacle, that also should be investigated properly, so that the control barrier function becomes able to avoid it. Okay. So in this lecture, what do we see? We first talk about the motivation behind control barrier function. We see that a control barrier function is a function that creates a barrier between safe and unsafe region, and then finally generate a control input so that the safety can be ensured. We talk about affine control systems, x dot equal to fx plus gx u, and later in the later half of the lecture we see that why affine control system is important. We talk about safe and unsafe set. We specifically spend time on forward invariance, because that's a mathematical concept which is very important to understand in the process of understanding control barrier function, because otherwise we cannot appreciate that how control barrier function ensures safety, right? So, quadratic programming problems are the optimization problem where control variable function is used as a constraint. Finally, we talk about advantage and limitation of control variable function. Okay, these are some papers which you can get in IEEE. Those are important to understand the concept of control variable functions. You will get very foundational argument that how control variable function is helpful, how it is built from general mathematical understanding, then how this can be used in different applications of robotics and other systems, autonomous systems. So I would request the students to go through this two papers, and we conclude this lecture here. See you in the next lecture. Thank you.